Let's review analyzing variances. So we're now going to compare two population variances. Sam and Eli are two amateur golfers trying to figure out who the more consistent golfer is. You compare scores from this year and you want to create a hypothesis test for this at a 0.5 significance level. Sam went golfing 10 times and Eli went golfing 9 times. So we have their data here. Now, just to be clear, what we're doing is trying to determine who is a more consistent golfer. We can see at a glance here that Eli is better. He's got lower scores. His average is probably lower. But we're looking for who hits more consistently. So to do that, what we're going to use is what is called our F-test. Our F-test follows the following formula. So we are dividing sample 1, which we'll call Sam, divided by sample 2's variance. So that, and just note that we may have to fit, it may not be Sam and Eli. In the F-test, the numerator is always the larger number. That's how you get your F value. So we will have to switch around whichever sample is larger. But before that, what we need to do is we need to determine the sample standard deviations. So for this formula, we're going to need to use the following for both Sam and Eli. So as you can see here, we need the sum of the observations squared, and we will need the the sum of the observations squared, and we're also going to need to have just the sum of the observations. So why don't we just set up a chart here. So we'll get the sums or the totals. And we'll go Sam squared and Eli squared there. So when we add all of Sam's scores up, we have 1,023. When we add up all of Eli's scores, we get a total of 890. We can now start squaring each of Sam's scores and putting them here. If you would like to use Excel for this, you can do that, but a calculator and it should work fine. Just put a little line here just to break it up a bit. It's getting a little tight. Okay. So for Sam's scores squared, add that up, we get 104,709. 791. And we can do Eli's now. We add up Eli's score squared. So now that we have our information, we can start entering it into our standard deviation formula. So we start with S1 for Sam. The sum of our observation squared is 104,791 less the sum of our observations, which we will square, oh, I see here that I've just forgotten something very important. We do need to divide these by our n. So we can do that here. We had 10 observations for Sam. And n minus 1 is 9. (1,023) squared divided by 10 . So our standard deviation for Sam, based on his scores, is 3.92. So let's do the same for Eli now. Oops. I did square it. I take the square root. I just forgot to put that in there. Okay. Sam had one less sample here. He had 9. Pardon me, Eli had one less. He had 9. And for Eli, we have a standard deviation of 9.67. So a lot of you may say, well, it's very clear now that we can see that Sam is the more consistent golfer. Sam has a standard deviation of 3.92. Eli has a standard deviation of 9.67. That could mean on any given day, there is a 68% chance that Sam's that's, because we're using one standard deviation, so we can show it here. So if the mean is here, and one standard deviation to the left, one standard deviation to the right, for Sam, here's his mean. He could do less 3.92 off his mean, or plus 3.92, and there's a 68% chance based on our sample that it will fall in this range. Whereas Eli, this would be negative 9.67 and negative plus 9.67. So Sam has a range of about 8, give or plus minus 4, or 3.92 from his mean. And Eli has almost 20, about 9.7 or 10 less, or 9.7 or 10 more. So you would think that it's quite obvious that Eli is the less consistent golfer. But what we need to do now is make sure that our range, our data, this isn't just chance, because this could be up to chance. So what we need to do is determine our F value to check and see if that's chance. Now, we need to do that. We need to just quickly discuss our hypothesis, because depending on if this is a single tail or a two-tail hypothesis test, it will check, or it'll depend on which distribution table we use. So for our hypothesis, we want to say that the population standard deviation, or the population variance, for Sam is equal to Eli's variance. So we're going to say the null hypothesis is that they're the same, consistency. The alternative is that they are not the same. So we know that if this is less than, so if we were to say Sam is has a higher variance, so less consistent, then that would be a single tail test, because we're only looking at one side of this. But we're just saying it's not equal to. So it can be either direction. So we have what's called a two-tail test. And that's important when we get to our F table. So F equals S, our standard deviation squared, so our variance, divided by our Sam variance divided by our Eli variance. Now our Sam variance is 3.92 and our Eli variance is 9.67. But if you remember me saying at the beginning, we always switch, so the higher number is on top. It must be that way. The numerator must be the largest number. So we're actually going to switch these to S2, S1. So F equals 9.67 divided by 3.92. That's right, 9.67, yeah, 3.92. So 9.67 squared is 93.5089. 3.92 squared is 15.364. We get an F value of 6.0852. Now we need to determine what is our F chart. So you'll see in your formula sheet that your F distribution table will have several different tables. And it all depends based on the significance level. We have asked for a significance level of 5% or 0.05. So we've set our significance level here. Now this is two-tailed. That means we can have a 0.025 significance level on this side and 0.025 on this side. So what we'll be looking for is the 0.025 significance. 0.025 higher and 0.025 lower. Because if we allowed significance of 5% on both sides, it would be a total of 10. So when we have a look at our F distribution table, we're going to use the 0.025. Now, they ask for 2 different degrees of freedom, your F table, and in this scenario, when you use the F score, your degrees of freedom are n minus 1. So the numerator degree of freedom is on the top side of the table, you'll see here, and the denominator is along the left side. Now, although it does say S1 and S2, remember we did swap these because the numerator must be the largest number. So for S2, which was our numerator, Eli had 9 observations, n minus 1. So S2, our second degree of freedom, would be 8, and degree of freedom for 1 would be 9. So our numerator is 8, and our denominator is 9. So now we've chosen the right table, and we just need to find where they intersect. So what our F score is, what we're looking for is our test statistic. What this chart gives us is a number. Now it's telling us at 0.025%, what is the test statistic that gives us exactly 95% confidence, or 5% significance on a two-tail. If this was one tail, this would just be, we would actually be having 97.5% confidence. But it's two tails, so we have a 0.05% significance and a 0.95% confidence. We have our numerator of freedom for our here at 8, and we're going down to our denominator degree of freedom at 9, and we can see that they intersect at 4.10. So 4.10. So at 4.10, according to our F table, this test statistic would be 95% confidence. Anything beyond this 4.10 would have a higher percentage chance. So we have an F of 6.08. So we can assume that this is up in the 99 to 100% range. So we do have very clear statistical evidence that we can reject this hypothesis and that the alternative is true. So we know that the two golfers are not the same consistency, and so that this sample was not chance, and that Sam is a more consistent golfer. He's got the smaller variance and smaller standard deviation.